Hey folks, how's it going? This is Rob coming to you live with a quick little walkthrough of homework quiz number 1. Now, originally the first time I did this through, I did discuss this homework quiz in class immediately following the break, but I did get some requests for the answers, so I thought that I would just take another second and walk through it. So this quiz was covering limits and one-sided limits. So 9.1, an introduction to limits. 9.2, one-sided limits. All right, and I apologize for any shadows that might get in the way. All right, folks, so I'm going to go ahead and get started. And as I go through, I'll talk about maybe some potential misconceptions that people had and try to hopefully guide you in the right direction. All right, so question number 1 and 2, in fact, asked us to compute the limit or state that it does not exist, okay? And so for a limit to exist, we know that the limit has to be the same from the left and the right, and I guess also has to exist on the left and the right as well. So in this case, what we have is we have x cubed plus 1 over 2x cubed plus 2. Now, when we say the limit exists or does not exist, one thing we might be looking for is, one, any signs that it would not exist based on the limits from the left and the right not agreeing. Typically, that tends to happen when you have a denominator of 0. But in this case, what we want to do is we first, as I said in class, want to try by plugging in 1. Okay, because the limit is as x approaches 1. So if we do that here, what we have is, let's try to plug in 1. So what we get is we get 1 cubed plus 1 all over 2 times 1 cubed plus 2. And that gives us, and sorry for any shaking there, 1 plus 1 on the one side. All right, and down the bottom, you get 2 times 1 plus 2. And so that gives us 2 up top. 2 plus 2 is 4 on the bottom. And that's 1/2. So this limit, so therefore we say the limit as x approaches 1 of x cubed plus 1 over 2x cubed plus 2 is 1/2. Okay? And in this case, if we were going to say, ask ourselves, well, does a limit exist or not? In this case, if I'm looking at it, there's nothing to really suggest it doesn't exist. All right, as the limit's going from the left and from the right, there's nothing about this function in and of itself, if you look at the top or bottom, that would be problematic. Again, we don't see, just from a straight up plugging in perspective, anything going to 0. You can tell that, again, since we discussed continuity, we know that any polynomial is going to be continuous for all x values in its domain. That's something we learned about in 9.2. So in this case, we have a polynomial up top, and that's going to be continuous for all x values in its domain, which means if we look at the top, the limit as the top approaches 1 should be the same as simply plugging in the value. And the same goes for the bottom as well. Okay, so in this case, we get the limit. Again, all you're doing is plugging in, so you're getting 1 on the top. All right, 2 on the top, 4 on the bottom for 2/4. In other words, 1/2. Okay, so if you need to take a second and kind of rewind that and take another quick check back, anything, go ahead and do that. I'll give you a couple of seconds, and then I'll move down to the next problem. All right, so the next problem we have is the limit as x approaches 0 of 2x squared minus 3x over x. Now, in this case, what I saw was I did see a lot of people plugging in, which is very good. So let's go ahead and try to do that. So if we plug in 2 times 0 squared minus 3 times 0 over 0, what we get is 0 over 0. Okay? And what a lot of people did right away is they wrote does not exist. Now, that might be okay, except for the fact that 0 over 0 in and of itself doesn't necessarily mean the limit doesn't exist. Remember, in 9.1, we had this whole thing with Smug Newton where he had, just as when we had tried to figure out how the limits work, he kind of threw this curveball at us with the idea that, well, now I'm going to give you a limit of 0 over 0. Okay, and so what we discussed in class is when you get the 0 over 0 phenomenon, what you want to do is you want to come back to your original function and see if you can rewrite it in a different but equivalent way. And so if I look at the original function, what I notice is I notice an x here, an x here, and an x here. And so what I'm going to do is I'm going to come down and I'm going to rewrite it as the limit as x approaches 0, and I'm going to go ahead and I'm going to divide everything I see here by x. And again, sorry for any shakiness that's going on there. So what that gives me is it gives me 2x when I divide the x squared by x minus 3. Okay, and so what that shows me is to calculate this limit is the same as to calculate this limit, okay, because this fraction or rational expression is equivalent to this right here. And so it's essentially the same to calculate either of the limits. And again, because this is a polynomial, what we know from the rules of continuity is that this is a continuous function, which means that the limit as x approaches 0 of this is the same as simply plugging in 0 into the function, okay? And what that gives us is -3. Okay, so therefore, the limit as x approaches 0 of 2x squared minus 3x over x is equal to the limit as x approaches 0 of 2x minus 3, which is equal to -3. Okay, so again, we're using our notions of limits. And remember, just because you're getting a 0 over 0 does not mean that something does not exist. Okay, remember, 0 over 0 is what we call an indeterminate value. All right, and kind of remember how I used that Siri example, asking Siri about this. Just because we're getting that, now this is what we call indeterminate because we don't know exactly the value. Is it 0? Because on top we have a 0, and when you divide 0 by something you get 0. Is it infinity? Because when you divide by 0 you usually get something that's infinitely large or almost not even a real number. Or is it infinitely many numbers, right? Because anything times 0 is 0, right? And that could be another definition of how you define a quotient. All right, and because there is no determined value, it would be called an indeterminate. Okay, so again, we're getting our limit being -3. So again, go ahead and take a second. If you need to rewind it or you need some time to soak that in, go ahead. And then I'm going to go and move on to number 3. Okay, so let's go ahead and take a look at number 3. Determine all the values for which the function is discontinuous. Okay, so we have x squared minus 2x over x squared minus 3x plus 2. Now, on this first homework quiz, I was a little bit lenient, as I said in class on this, but what we got to go ahead and we got to unpack this. So what we're looking for when we think of discontinuous, well, usually discontinuous means any point where if we were to graph this function, we would have to pick up our pen, right? Any kinds of holes in the graph, any kinds of vertical asymptotes, or in other words, x values that make the function undefined. Okay, and undefined is a little bit different from a 0 over 0 situation. So what we're going to have to do is let's go ahead and try to break this down. So what I notice is I notice an x squared and an x squared, and I also notice that there's a greatest common factor here. So what I'm going to do is I'm going to go ahead and I'm going to break this numerator down as so. And now I'm going to see, right, if I can factor the bottom. Now, this whole skill of factoring is extremely important in calculus. We always have to be able to be ready to express things in different ways, okay? And so as it turns out on the bottom, what I get is I get x and x for the x squared. And now I think, well, what numbers will multiply to positive 2 and add to -3? And that's -2 and -1. And now again, I see an opportunity for me to cancel these out because I have this common factor of x minus 2 and x minus 2. And what that gives me is, so these are equal here, and now what that gives me is x over x minus 1. And when I do that, I can now see that if x is equal to 1, I'm going to have this thing be undefined, and that's going to be a point of discontinuity, okay? A point where I can't graph it without picking up my pencil. Now, if we were to graph this out with limits, what we'll see is that as the number approaches, as this thing approaches 1 from the right, okay, x is bigger than 1, meaning the bottom is going to be positive and the top is being positive. So as we're going to -1, on one side, it's going to positive infinity because you've got a positive divided by a positive. But as you come from the left, x is less than 1, so this number here is going to be less than 0, right? Because a number that's less than 1, right, like 0 or 0.5 or 0.75, when we subtract 1, we're going to get a negative number. So we'll have a situation going to negative infinity, and what you can see, right, so this is like x equals 1. So what this is telling us is that the limit does not exist when x is equal to 1, and that's a cool little thing right there, right? So here's another example of a limit not existing, right? As we go from the left, we get negative infinity. As we go from the right, we get positive infinity, all right? And that's going to be a situation where the limit does not exist. All right, so anyway, our idea is the function is discontinuous at x equals 1. On the quiz the first time around, I was very lenient and I allowed you to say x equals 2. But x equals 2 is not necessarily a point of discontinuity. We know now one way is that if I had actually rewritten it as so, what I would have gotten is I would have gotten 2 over 1. Right? If you plug in x, you get 2 up top. 2 minus 1 is 1 on the bottom. So you can see that if you plug in 2, you actually do get a defined value. The misconception here about 2 being a point of discontinuity is that it appears that if you plug in 2 in the bottom, right, you get 0. So it appears that you're getting 0 in the denominator, bad. But in fact, because we now know we can rewrite it like that, 2 is not actually a point of discontinuity. And that's where we kind of got into the nitty-gritty. And so the first time around, because I explained it in a confusing way, I feel like I did give you a little bit of leniency here. But from now on, right, we're looking to really kind of simplify top and bottom as much as we can before jumping to that conclusion, all right? Because 0 over 0 does not necessarily mean a discontinuity, right? And in this case, if we plugged in 2, we would have gotten a 0 over 0 situation. All right, so the idea is we want to simplify first before seeking out those points of discontinuity. And whenever you see one clear greatest common factors, such as x and x, or in general, squares, that's got to be a sign we got to look to factor, right? That's something I got to assume that you're just going to do now that we're in calculus. All right, so take a second and if need be, kind of clarify anything, kind of run back the tape if needed. I'll give you a few seconds before I move to our final question. All right, our last question is the oxygen content as a percent T days after organic waste has been dumped into a pond is given by this function here. Okay, so we're supposed to use the intermediate value theorem to show that at some point the oxygen content of the water had to have been 80%. So remember, if I plug in a number, so if I plug in 0, for example, just to help you understand what this function is a little bit better. What I get is 100. Okay, so this is like I just dumped the stuff in, right? So if I plug in 0, this will be 0, this will be 0. So what I get is 100, right? Because again, 0 plus 0 plus 100. And the same thing is going to happen on the bottom. And 100 over 100 is 1. So it's 100, right? So what that says is when I first dump the stuff in, the oxygen content is 100%. So that's actually helped me solve the problem, right? Because the intermediate value theorem states that given a continuous function, right, if I have a number, a plug-in number that's less than 80%, and a plug-in number that's greater than 80%, because the function is continuous, at some point there had to have been a t-value where the oxygen content or the output hit 80%, right? Because if I have a function where I have an 80 and a 100, right? Let's say this is my 100 and this is my 80. Because it's continuous, it has to hit every single point between the 80 and the 100. And I'm not saying this is what it looks like, but this is the concept of what the IVT says. So essentially, we need to find an input where the value is greater than 80, and we've got that, right? We know now that f of 0 equals 100. So now what we might want to think about is what other inputs could we supply where we need to undershoot? We need to get lower than 80%. And what I'm thinking about is, and it doesn't matter, right? Don't need to say what point, we just need to prove that at some point it happens. So what I notice here is I see 10s and 100s. So I'm going to plug in 10, okay? Because 10 is easy to square, it's easy to multiply by 10, and let's see what I get. So if I plug in 10, I've got 100, and I've got 10 squared plus, and essentially another 10 squared plus 100. Okay, and again, sorry for any shakiness there. And on the bottom, I have a similar thing. I'm trying to write as slowly as I can so I don't get too many shakes. Okay, so let's simplify this out. And on the top, what I have is 100 plus 100 plus 100. Then on the bottom, what I get is 100 plus 200 plus 100. And that's the other reason why I like 10 in a situation like this. Because again, the value you plug in does not necessarily matter, especially because we're not given a domain, right? Sometimes with some of the problems we're given, like the train problem, had an implied domain, right, of between 0 and 30, but here there's no specific domain. So we have a lot of options from which to choose, okay? So let's try to continue on this one. So we have 100, and now we have, I'll just make that clear, we have 100 plus 100 plus 100, and then we have 100 plus 200 plus 100. Okay? Now, 300 out of 400 we know is the same as 3/4. And 100 times 3/4 is 75. Okay? So this is what we've got here. We know that we have 2 points now on the graph. We have 0, 100, and we have 10, 75, and because this is a continuous function, right, presumably, we know that because at one point it was 100 and at another point it was 75, then at some point between 0 and 10, the function had to have obtained the value of 80%. And that's all you really need to show in a problem like this, all right? Because again, the IVT says, the intermediate value theorem says, that given a continuous function and given two outputs, the function will obtain all the values between the first output and the second output, okay? So in this case, because we know that 0, 100 is a point, and 1075 is a point, this function has to, between 0 and 10, hit every single real number value between 100 and 75. And if we think about it, based on what we know about continuity, we know it has to be true, because if the function is continuous, then that means that there's no way that to hit any of these values, right? If we were to say miss 99, well, the only way we could do that is if we picked up our pen and shot over 99. But what we know is if the function is continuous, right, we can never pick up our pen when we're drawing out that function. Okay, so I hope that you found this video to be informational, and I hope that it helped you maybe elucidate some potential misunderstandings you had with this problem and with the others. And again, I really welcome you to reach out to me. You can reach me at robert.moray, that's M-O-R-A-Y, at umb.edu, okay? And when you reach out, please, 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 I can't say please enough, try to send me some questions that you have. And when you send me your questions, try to make those questions as specific as possible and try to send me your work, all right? Because the idea of this class is I want to really help you, right? That's my goal. That's why I've got this job, is to help you learn. And in order to help you learn, I got to know where you're at, right? So for example, let's say you were on this problem. You said, hey, Rob, look, I know that I've got a IVT. I know that initially it is 100. I plugged in 100. I got this. Maybe you send me your picture of this. This is your picture. But I don't know where to go from there, right? I know it's got to hit 80% at some point, but I don't know where to go from there. then maybe that helps me give you that guidance. Maybe that helps me say, okay, well, look, the intermediate value theorem says that we've got an output of 100. We need to prove it hits 80, so we need to find a value that's less than 80. Is there a good number that you might plug in? Since it doesn't really matter necessarily, that would help you do that. Think about what numbers we've got as coefficients. All right, that lets me give you those important guiding questions so that you can kind of put the pieces together on your own. All right, and so you can take kind of charge of that. All right. So again, the more you can help me, the more I'm here and I can help you, all right? Because if I just give you a run through of the problem, like a plain vanilla run through, that's just me doing the work for you, right? And obviously, when we do these tests in the long run, I'm not gonna give you the same exact question, right? So you're gonna have to know how to demonstrate the same ideas with other kinds of contexts, all right? So I really hope, again, this video, you found it enlightening and you've kind of walked away with it with more than when you came in. Again, feel free to reach out anytime. All right, I'm always here to help. And have a wonderful week. Good luck, and you can do it.